In this video, we're going to look at an example and conduct a hypothesis test. We're going to go through our steps that we discussed at the end of the previous video. So Nexium. Nexium is a drug that can be used to reduce the acid produced by the body and heal damage to the esophagus due to acid reflux. The manufacturer of Nexium claims that more than 94% of patients taking Nexium are healed within 8 weeks. In clinical trials, 213 of 224 patients suffering from acid reflux disease were healed after 8 weeks. Test the manufacturer's claim at the alpha equals 0.01 level of significance. So, we're going to follow our process for conducting a hypothesis test. So let's take a look at this. So bringing this back in, first of all, we can use our steps for this process if these conditions are met. So we have to have a sample obtained by simple random sampling. Now, it doesn't specifically say that in this problem, but again, we're dealing with a clinical trial. We have 213 out of 224 patients. I will assume that those 224 patients were randomly selected since it's a clinical trial. So I'm going to give a benefit of a doubt here, even though it doesn't specifically say that in the problem. So I need to check n times p naught times 1 minus p naught, n times p naught times 1 minus p naught to make sure that's 10 or bigger. Well, p naught's going to be this 94%, and n is 224. So I'm checking my conditions. So is n times p naught times 1 minus p naught, is that 10 or bigger? Well, so I'm going to take 224 times 0.94, again 94%, times 1 minus 0.94. If you wanted, you could just say that's 6% or 0.06. So if I have 224 times 0.94 times 0.06, again 0.06 is just what 1 minus 0.94 is, and so that is 12.6336, and that is bigger than 10, so we meet that condition. And the third condition is that the sampled values have to be independent of each other. And so in order for that to happen, we generally make sure that our sample size is less than 5% of the population, and certainly 224 patients is less than 5% of the population of patients. So we'll accept that that's true as well. So the main one that we're going to check here is this condition, if that needs to be bigger than 10. So now that we have that decided, we need to determine the null and alternative hypotheses. Well, what is it that we're actually trying to do? We're testing the manufacturer's claim. And the manufacturer's claiming that 94% of patients that take Nexium are healed within 8 weeks. So the null hypothesis is that the proportion of patients who are healed within 8 weeks is 94%, or 0.94. And so what's our alternative hypothesis going to be? Well, in this particular case, the manufacturer of Nexium is claiming that more than 94% of patients are healed within 8 weeks. So that more than tells us that we're going to use greater than in our alternative hypothesis. Now, so actually what we're doing is we're testing the claim as our alternative hypothesis in this case, and the equals is the null hypothesis. So basically, if we conclude that this is true, we're going to say that what the manufacturer is stating is true. If we conclude this is false, then we're going to say that what the manufacturer is saying is false. So if we accept that the null hypothesis is true, then that will mean that the manufacturer's claim is not correct. And if we conclude that the alternative is true, then the manufacturer's statement is correct. So we've done step 1. We've determined our null and alternative hypothesis. Step 2, we want to select a level of significance depending on the seriousness of making a type 1 error. So in this case, we've been told that we're supposed to use alpha equals 0.01. Notice that that is really small. We're only risking a type 1 error with a 1% probability. Well, that's often the case in medical studies because we want to make sure that we don't make a type 1 error. We don't want to end up rejecting the null hypothesis when the null hypothesis is actually true. So it would be a serious consequence, perhaps, of making a type 1 error, so we want to make sure that doesn't happen. Step 3. Well, now I'm going to split this up, and depending on whether we're dealing with the classical approach or the p-value approach, and I'm going to do it both ways. So let's start by looking at the classical approach. So with the classical approach, first of all, notice that we have a right-tailed test. Because our alternative hypothesis is greater than, we're going to be dealing with a right-tailed test. So I'm going to draw the standard normal distribution, and I'm going to be interested in what's going on in this right tail. Here is 0. This is the standard normal distribution. I need to figure out that critical value right there if this area in the right tail is alpha equals 0.01. So again, how can I go about figuring out what that critical value is? Well, we've studied this before. I can use the inverse norm command on my calculator. I can use the standard normal table, or I can use the normal calculator in StatCrunch. Any of those will give me the same critical value if I do it correctly. So I'm going to use the inverse norm command on my calculator. Now again, just as a reminder, I have a newer calculator that lets me do things that you may not be able to do on your calculator. So if I go to inverse norm, my area is 0.01 in the right tail. So I'm going to choose 0.01 as the area in the right tail. And so that value is going to be about 2.326. So this critical value is 2.326. Now again, if you had an older calculator, then you always have to put in the area to the left. This area to the left would be 0.99, so I would do inverse norm of 0.99 in order to get the 2.326. But depends on your calculator. And again, you could also use the standard normal table, or you could use the normal calculator in StatCrunch, whichever you prefer. So I have my critical value. Now I need to calculate the test statistic. So I need to calculate Z0. In order to calculate Z0, I need to know what my test statistic is. So my test statistic, Z0, is going to depend on what p hat is. So I really don't want Z0 there, I want p hat. So p hat is going to equal 213 out of 224. Well, if I bring back in my calculator, 213 divided by 224, that is 0.9509 if I round to 4 places. I'm carrying that out several places because I don't want rounding to be an issue. So it's looking like in this sample we got 95% of the patients who were healed within 8 weeks compared to 94%. So is that statistically significant? Is that enough to say it's actually greater than 94%? Or could this possibly be just because of variation in samples? So my Z0, again, is going to be p hat minus the p from the null hypothesis divided by the square root of p from the null hypothesis times 1 minus p from the null hypothesis divided by n, the sample size. So now that I know what p hat is, that is 0.9509 minus 0.94, that's the p from the null hypothesis, divided by the square root of 0.94 times 1 minus 0.94 over 224, because that's what n is. So if I bring back in my calculator, parenthesis 0.9509 minus 0.94, close parenthesis, divided by the square root of 0.94 times 1 minus 0.94, which is 0.06, divided by 224, which is the sample size. So I get 0.687, let's say. 0.687. Well, comparing that to my critical value of 2.326, 0.687 is over here to the left of it. It did not fall over here into the unusual area. So my conclusion, do not reject the null hypothesis. So I'm not able to reject that it's 94%, so I'm not able to say that it's greater than 94%. So as far as I can tell, I got this result maybe just because of variation in sampling. It's not statistically significant. This result is not statistically significant. It's not different enough from 0.94 to conclude that the 0.94 is wrong and that in fact it's greater than 0.94. Now what if we did the p-value approach? With the p-value approach, I still have to calculate z-naught. So I would still calculate and get that z-naught equals 0.687. But in this case, to find the p-value, because it is a right-tailed test, the p-value would be the area to the right of 0.687. So this area right here would be the p-value. So if I find the area to the right of 0.687, and how do I do that? Well, I can use the standard normal table to do that. I can use my normal CDF command on the calculator to do that, or I can use the normal calculator in StatCrunch to do that. So using whichever one of those methods you prefer, you can find the area to the right of 0.687. So if I bring in my calculator, I'm going to do normal CDF, and I'm finding the area to the right of 0.687. So I'm going from 0.687 to a big positive number. The mean 0, standard deviation is 1. And so I get 0.2460. So this area right here is 0.2460. So my p-value is 0.2460. Now, because my p-value, 0.2460, is bigger than 0.01, my level of significance, we do not reject the null hypothesis. So the question was, well, we were just asked to test the manufacturer's claim. Well, the manufacturer of Nexium was claiming that more than 94% of patients taking Nexium are healed within 8 weeks. While we did get 95% in our sample, that was not statistically significant. So we were not able to reject that it's 94% and say that it's more than 94%. So as far as we can tell, the percent of patients who are healed within 8 weeks is not more than 94%. So it may be 94%, but it's not more than 94% as far as our test goes. So let's take a look at another example, but we'll do that on a new video.